Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In the last video, we introduced a technique called logarithmic differentiation, which allowed us to bypass complicated product and quotient rules by taking the log of both sides of the equation, simplifying it using our log laws, and then using implicit differentiation to find the derivative. In this video, we're going to take a look at a few intermediate level problems involving logarithmic differentiation and some common exam problems that could show up. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first example, we're going to differentiate this messy looking equation here. Notice that for this problem, it is possible to use your quotient and your product rule to find the derivative, but it's going to get pretty messy. So we're going to apply our logarithmic differentiation here, which means we're going to take the natural log of both sides. That means we get ln of y is equal to ln of the right-hand side, which is x cubed times x squared plus 1 to the power of 1/2 over x minus 5 to the power of 4. And now we're going to use our log laws to split this up into separate logs, which means ln of y is equal to 3 times ln of x plus 1/2 times ln of x squared plus 1 minus 4 times ln of x minus 5. And now we're going to take the derivative with respect to x on both sides of this equation. So we go d by dx of this and d by dx of this. The left-hand side is going to be 1 over y times dy dx. And then the right-hand side, we're going to get 3 times 1 over x plus 1/2 times 1 over x squared plus 1. And then chain rule says we need to multiply this by the derivative of x squared plus 1, which is 2x. And then we have minus 4 times 1 over x minus 5. And now isolating dy dx, we end up with this is equal to y times 3 over x plus x over x squared plus 1 minus 4 over x minus 5. And then the last step we can do is substitute in the equation for y back into y, which means our final answer here is going to be x cubed times the square root of x squared plus 1 over x minus 5 to the power of 4. So that's our y. And then we multiply that by 3 over x plus x over x squared plus 1 minus 4 over x minus 5. So this would be our final answer. Now let's take a look at our next example, which is an AP/IB style problem. Here we want to find the equation of the tangent line to y at x is equal to e. Now a quick note, y here is equal to x to the power of ln of x. So our power here is not just a number, it's in terms of x, which means our power law here doesn't work. So the only way for us to take the derivative here is through logarithmic differentiation, which means we get ln of y is equal to ln of x to the power of ln of x. And now we can use our log law to peel the power down, which means we get ln of y is equal to ln of x times ln of x. And then we can go ahead and simplify this into ln of y is equal to ln of x all squared. And note that this is not the same as ln of x squared, so make sure you have your brackets around your ln of x. And now we're ready to take the derivative with respect to x on both sides of this equation. So the left-hand side, we're going to get 1 over y times dy dx. And then on the right-hand side, we're going to get 2 times ln of x. And then we're going to use chain rule and multiply this by 1 over x. And finally, we can go ahead and isolate our dy dx, which end up being dy dx is equal to 2 times y times ln of x over x. And now we want to find the equation of the tangent line at x is equal to e. So which means we're going to need a point. So our point is x is equal to e, which means y is equal to e to the power of ln of e. And ln of e is just 1, so our y value here is e. So which means our point here is e, comma, e. And next, we need our slope. And to find the slope, we just need to calculate our dy dx at the point e, comma, e. And this is going to be equal to 2 times e times ln of e over e. So this is 1, which means we get 2e over e. So our slope here is equal to 2. And now putting this all together, using our point slope form, we end up with y minus e is equal to 2 times x minus e. And that would be the equation of the tangent line to y is equal to x to the power of ln of x at x is equal to e. Now for our third example, we want to find the derivative of x to the power of x squared. And just like the last example, the power rule doesn't apply here because our power is not a number, it's in terms of x, which means we have to use logarithmic differentiation here. So we're going to let y be equal to x to the power of x squared. And then we're going to take the natural log of both sides. So we get ln of y is equal to x squared times ln of x. Next, we're going to take the derivative with respect to x on both sides of this equation. So we get 1 over y times dy dx is equal to, and here we're going to have to use our product rule. So we get 2 times x times ln of x plus x squared times the derivative of ln of x, which is 1 over x. Now isolating dy dx is going to give us, this is equal to y times 2x times ln of x plus x. And now the last step is again substituting in the expression for y back into y. So we get dy dx is equal to x to the power of x squared times 2x ln of x plus x. Lastly, we're going to take a look at a more complicated example. So what you see on the screen here, this is known as Knuth's up arrow notation, and it's used to represent repeated exponentiation. So then the double arrow here means that we are taking x to the power of x to the power of x, a total of 3 times. And this is commonly referred to as titration or a power tower. And just like before, we're going to differentiate it using logarithmic differentiation. So we start by letting y be equal to x to the power of x to the power of x. Then we're going to take the natural log of both sides, which means we get ln of y is equal to x to the power of x times ln of x. And again, just like before, we're going to take the derivative with respect to x on both sides of this equation, which means we get 1 over y times dy dx is equal to, and here we have to use our product rule. So we need to take the derivative with respect to x of x to the power of x, multiply that by ln of x, and then we add x to the power of x times the derivative of ln of x, which is 1 over x. So notice how I've left this as d by dx of x to the power of x, and this is because in order to find the derivative of that, we need to again apply our logarithmic differentiation. So we're just going to do that on the side, and then we can go ahead and substitute it in. So I'm going to box that, and then go to the side, and say d by dx of x to the power of x. So we're going to find that over here, and what we're going to do is we'll let u be equal to x to the power of x, take the natural log of both sides, so ln of u is equal to x times ln of x, which means 1 over u du dx is equal to ln of x plus x over x. And then finally, isolating our du dx, we get this is equal to u times ln of x plus 1. And now substituting u back in, we end up with this is x to the power of x times ln of x plus 1. And now we're ready to take this and substitute it back into our original equation, which means we get 1 over y times dy dx is equal to x to the power of x times ln of x plus 1 times ln of x plus x to the power of x times 1 over x. So I'm just going to box this thing here so that we know that we found this by taking the derivative of x to the power of x. And now finally, the last step here is isolating dy dx, and this is equal to y times x to the power of x times ln of x times ln of x plus 1 plus, and we can simplify that second part of this equation. This is just x to the power of x minus 1. And again, the last step is substituting the expression back into y, which means we end up with x to the power of x multiplied by x to the power of x ln of x times ln of x plus 1, and then plus x to the power of x minus 1. And this would be our final answer. And now let's do a quick recap of what we covered in this video. We learned how logarithmic differentiation can help us handle ugly functions because it's the most efficient tool for functions involving multiple products, quotients, and powers, as it allows us to bypass nested quotient and product rules. And not only that, but we learned that it is the only way for us to deal with equations that have variable bases and exponents, because standard power and exponential rules fail there. So taking the log of both sides and moving the exponent down is the only way for us to differentiate. And now it is your turn to give this a try. Can you find the derivative of the equation on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.